just like for first order ODEs, where we're able to classify our equilibrium solutions as stable, unstable, bistable, we can actually do the same thing here as well. So let's classify the equilibrium points of the system we just studied. X prime equals minus x plus xy, and y prime is minus 8y plus 4xy. So first of all, related to the previous video, we find the equilibrium points. And this you can watch the previous video, and we found 0, 0, and 2, 1. Just by setting x prime and y prime equals 0. Now, the good news is we don't even need to draw a picture here. We can just find the classification directly. So let's first do it for 0, 0. And it turns out all we need to do is to find the gradient of f at this point. So step 1. Find the gradient of f at 0, 0. Why? Because the gradient, it's the derivative. So it turns out the derivative at that point will tell us whether solutions move towards the origin or away from it. I'll explain this at the end. So in order to do that, let's first find the derivative at xy. So once again, differentiate the hell out of everything. Minus x plus xy with respect to x, minus x plus xy with respect to y, and then minus 8y plus 4xy with respect to x, 8y plus 4xy with respect to x, and minus 8y plus 4xy with respect to y. Again, very complicated, but it'll simplify, you will see. So if you do that, I believe you get minus 1 plus y, and then minus, or just x, and then 4y, I believe minus 8 plus 4x. But much easier now. So this is already simplified, but we can actually simplify this further because we need to plug it in at the equilibrium point. So now let's do the gradient at 0, 0. So gradient of f at 0, 0. So that becomes minus 1 plus 0, 0, 4 times 0, minus 8 plus 0, which becomes minus 1, 0, 0, minus 8. Which notice this becomes a constant matrix that doesn't depend on x and y anymore. And it turns out the trick here is to calculate the eigenvalues of this matrix. So step 2. So the eigenvalues of A, which is minus 1, 0, 0, minus 8, you don't even need to do any calculations, because in this example, we're lucky it's diagonal. So it's just the diagonal entries. R. So first of all, lambda equals minus 1 and lambda equals minus 8. Now, what do we do with those eigenvalues? The important thing, as you see, are the signs. So in this case, we have 2 negative eigenvalues. So again, just to recap what we have so far, we took the derivative of f, we plugged in our equilibrium points. that gives us a matrix, and you just look at the signs of the eigenvalues of that matrix. And here's the fact. So what do our eigenvalues tell us? So if the eigenvalues of A are, in this case, both negative, or we'll see they could be complex, so or negative reapart. What this means is solutions near 0, 0 go towards 0, 0, which means that our equilibrium point is stable. Then our equilibrium point in general AB is stable. If they're both positive, it means solutions will move away from the equilibrium point, and that would mean unstable. Positive or positive. Real part, then AB is unstable. And then we could have mixed eigenvalues. So one positive, one negative. One negative. This is called a saddle. So I'll draw a saddle point very soon. But it's really the equivalent of bistable. A saddle. And finally, if one of the eigenvalues is 0 or purely imaginary, then this is called degenerate. So else again, either 1, 0 eigenvalue or purely imaginary. I think lambda is plus or minus I, then AB is degenerate, or sometimes called neither stable. Unstable. So, woof. Just be careful though of this last one, because I'll loosely use it. So on the exam, you would get full credit by saying degenerate, but sometimes based on the context, I will still call it stable or unstable, but this we'll see. So again, this is sort of the recipe. You find, again, the derivative, you plug in your equilibrium points, and you look at the eigenvalues. If they're both negative, then it's stable. If they're both positive, then it's unstable. If one is positive, one is negative, then it's a saddle. Okay. So here, we have stable. So here, 0, 0 is stable. And let me do the second equilibrium point now. And then I will explain why all this works and like what a saddle is and why we consider also complex things. So case 2, I believe the equilibrium point was 2, 1. So once again, I would like to remind you our derivative at xy, I believe it was -1 plus y x 4y and -8 plus 4x. So now let's do the gradient at 2, 1. So that is -1 plus 1, and then 2, 4 times 1, and -8 plus 4 times 2. Again, I just plug in x equals 2, y equals 1. And then this gives you 0, 2, 4, and 0, I believe. So that is our matrix. And then we want to look at the eigenvalues. Here, unfortunately, we have to calculate it because it's not diagonal. So a minus lambda I, that becomes minus lambda 2, 4 minus lambda, which is really minus lambda squared minus 2 times 4, which is lambda squared minus 8. You set this equal to 0, and you get lambda is plus minus √8. So in this case, we have 2 eigenvalues, one being positive and one being negative, which according to our recipe, it tells you that our equilibrium point is a saddle. Okay. And now let me explain to you a little bit why this works. So kind of why this works. This works. And again, let's go back to 0, 0, where we found both eigenvalues to be negative. I think lambda was -1 negative and lambda was -8 negative, and we said it was stable. Because really the question is, we have our equilibrium point 0, 0. What happens to nearby solutions? Will they get sucked into 0, 0 or get sucked away from it? Now that is for our system x prime equals f of x. It turns out the system x prime equals ax, where a was that matrix, is very similar to the original system. And for x prime equals ax, the eigenvalues -1 and -8, if you draw the phase portrait, solutions do go towards 0, 0. So that you can draw the phase portrait and you find the solutions do move towards 0, 0. But now, because x prime equals fx is similar to x prime equals ax, so both are similar, it actually tells you that the solutions also behave the same way. So if for the right-hand side, solutions get sucked into the origin, the left-hand side, solutions also get sucked into the origin. And that's why it's still true that 0, 0 is stable. So let me recap. So for x prime equals ax, solutions get sucked into the origin. But because both systems are similar, for the original one, solutions also get sucked into the origin. So 0, 0 is stable. The next thing I want to address is, why do we say negative real part? Why is this still stable? Real part. Think like lambda is -2 plus -3i. Well, in this case, if you draw the solutions, then they will spiral inwards. Spiral inwards towards the equilibrium point. And it's still true that solutions near the equilibrium point get close to the equilibrium point. So let's say this is maybe 0, 0. And that's why we still call it stable. Last but not least, what in the world is a saddle? We actually drew this before. So in other words, you might ask, what is going on at 2, 1? So let's just recenter this, and that is 2, 1. Then, because one eigenvalue is negative, on one side solutions get into it, and because another eigenvalue is positive, solutions move away from the other side. So we do have the picture that we did before. And because it's sort of both stable on one side and unstable on the other side, that's why we call it a saddle. It's stable on one side, unstable on the other. And you'll see in our population model that we'll do in the future lecture, we'll see those saddle points are actually very important in determining the behavior of the populations.